Right, so let's get the equation. So to get the second independent solution, first we look at the condition, what we mean by independent, or how to check whether two solutions are linearly dependent or independent. Okay, so the first is this general discussion. Say if you have n function, right? So I think you're using textbook, you have n functions, so phi 1, that depends on x, phi 2, x, altogether phi n x. You have phi n solution whether they are solution of differential equation, doesn't matter. Your n solution, you want to know whether they are independent to each other or not. So when we say they are linearly independent, which means any one of them cannot be expressed as a linear combination of the other, or the other way around. If it's linearly dependent, then we can find a linear solution relating all of them. And if that is the case, then they are dependent. So if you have I think the coefficient is called that is a string choice. K doesn't matter. I mean, then if you multiply k sub 1, y sub 1, k is just a constant, plus k sub 2, phi sub 2, plus k sub n, phi sub n. Or you can say this is sum over n. But we already have n, so I 1 to n, k sub I, phi sub I. That equals to 0. Right. If you can find parameter a k sub 1 to k sub n that satisfy this one for all x for all x over a certain domain, right? It doesn't have to be defined. Depends on how these functions are defined over a certain domain, over a certain domain, or right. So if that is true for all x, then they are linearly dependent. Okay, and to check that they to be, I mean, just using that is a little bit too abstract to determine whether they are determined or not, whether this solution exists or not, or the solution of k exists or not. So you have k parameter, and to show that you can find this parameter, you need n solution. Like a k parameter has n of this k. Your k sub 1 to k sub n, you have n of them, and you have n variables, so you need n solution. So to get more solution, you just take derivative. Say this is true, then you can say sum over I 1 n. Just take derivative by 1, phi pi will also be 0, and likewise phi double pi by double pi. It's all a function of x. That also 0, so and so on. And altogether, you need n equation. So originally you have 1. The first derivative is the second solution. The second derivative is the third solution. Then to get n equation, you need the final one is k sub I pi to the n minus 1 derivative x equals 0. Right. That gives you n equations for n unknown. It's okay. So that is just straightforward, right? And now to get the condition, first you can write that as a matrix equation. All this equation from this one to all this, you can combine to this a matrix equation. Now you want to solve case of 1, case of 2, all the way to case of n, right? And the right-hand side is 0. And the coefficient now is phi sub 1, phi sub 2, and phi sub n. And the next equation is phi sub 1 pi, phi sub 2 pi, phi sub n pi, right? And so on. And the last equation is phi to the n minus 1 derivative, phi sub 1, phi sub 2 to the n minus 1 derivative, and phi sub n to the n minus 1 derivative. Is that okay? They write it as a matrix form, well, a matrix equation, right? It's not that. And now when you, after you write it like that, you know the condition for solution, right? And what is that? In terms of using this equation, matrix equation, what is the condition for the existence of solution? Because the right-hand side is 0.
It should be
Dot product, but determinant is 0, yeah. So the determinant of this matrix is 0. So basically now this is the equation, now the determinant, and we have a name for that. This is called the Wronskian. Wronskian is just this one. Just copy all this. A lot of writing to repeat that, but just copy this matrix in here and take the determinant of this matrix, and we call that the Wronskian. And if this is 0, then you get at least that's that the solution exists, and which means that these n solutions are not independent; they are dependent actually, because based on this summation of k times phi. Okay, so the condition for linear dependent is the Wronskian is 0. So the other way around is if the Wronskian is non-zero, they are linearly independent, because you cannot find a set of parameter k to satisfy this this equation. And also this is required to have for all x, right, over this domain, right? And so you need to solve for that. This has to be 0 over this thing. Or the other way around is W is non-zero over this domain. And sometimes it can be accidentally be 0. But that is not enough to solve for k, because that only exists for one or some particular x. So if the Wronskian is generally non-zero, sometimes it accidentally 0 over a certain range, a certain isolated point, then it's still linearly independent. Okay, so that's the condition. All right, so this Wronskian is what you need to check whether they are independent or dependent. And I think this is simple enough that we don't need to go through the solution. I mean, examples. There's some simple example whether they are independent or dependent. It's okay, but that is the general idea. It's dependent, because you can find a set of k to satisfy this equation over for all x. Okay, and that is what we mean by linearly dependent. So this equation means any one of them, they are phi sub 1, can be expressed as a linear combination of the other phi sub 2 to phi sub n, which means they are not, phi sub 1 is not independent of the other phi, right? And likewise, you can look at it the other way, but that's the equation to say this is linearly dependent. Okay, and